Let's talk about the another very important concept in the OpenFOAM, that is the function object. Okay, so what we can do with the function object is following things. We can look at the mix main value and in entire domain or any of the patch. Okay, so sometime it is very handy to identify if inside the code or inside the any geometry anywhere any problem is there or not. What I mean to say is something like that way. Let's say we create a mesh, okay, and we have a little bit poor quality mesh, okay, and then also we started running the simulations, okay, but when we started, maybe later on it start diverging. So if when it start diverging, definitely its max min value going to be shoot out, okay, and so if we try to plot this max min value, it give us the idea, okay, what exactly happening with the u v w, or maybe the pressure or temperature, or what is going first in the divergent trend. Okay, so it gives us sometime very good idea about how the simulation is progressing. Okay, so not only that, let's say we are working on, let's say, inflow outflow type of the things, okay, or we have a multiple inlet and multiple outlet type of the things. So with the help of this function object, we can calculate very quickly the mass flow rate of different patches, and it gives us the idea either we are satisfying the continuity or not. Okay, so all this peripheral thing we can do very quickly with the help of this function object. Another very important is this probe that you already started using it. So with the help of the probe, we can monitor the our field variables on one particular points, and it gives us the very good idea about the convergence of the our problem, as well as it facilitates certain type of the post processing as well. So when we are working with the turbulent class of the flows, then this probe gives us the idea either the our flow become fully turbulent or not by looking at the this probe data. So it is not very quick way you can observe that, but we have to take the probe data, we have to do the FFT, and when we do the FFT and we plot it on the log scale, okay, then you can look at the energy spectrum, and if the energy spectrum is following -5/3 law, then you can say, okay, now my flow field become fully turbulent. So all these things we discussed during our advanced module, okay, but at that point of time we going to use this probe very rigorously. So that is one another thing. Then we have field averaged. So that is a very important concept in the CFD. If we are working with the transient calculation, then field average give us the statistic as well as averaged flow field. Okay, so sometime we want to compare our result with, let's say, any of the experimental data. Then normally experimental whatever the data we get is either in the mean, or that means in the time average domain, or with the statistical data. So if we going to use this field average, it help us to compare our result with the available open literature result. Then forces and force coefficients. So these force coefficients allow us to calculate CDCL value. So it is very important quantities, both to compare our data for external aerodynamic, and these forces give us the idea different forces, viscous forces, pressure forces, how it is applying on any of the domains. So normally these forces is very important when we are working with the FSI class of the simulations. Okay, at that point of time we have to check what class of the forces is applying on the particular membrane or particular let's say flexible domain, and with the help of that we can tune certain parameters. Okay, so that is how one can look at this all different prospect of this function objects. Okay, important part of the function object is that we need not to recompile anything. It is readily available. We have to just plug in all the required things inside the control dict file. So let me show you the one very nice control dict file that cover more or like all the aspect of this function object. Okay, so this is our regular all the entries. So all the function object is under the umbrella of functions. Okay, so you to write the function, and under the function we try to keep certain function object. Okay, so here is the few sample example of function objects. So inflow in inlet mass flow rate, if we want to calculate, then we say, okay, it is a type is a phase source. Okay, so either we want to calculate in entire domain, then the type is the cell source, but here we want to look at, let's say, on any of the patch incoming flow, then we say okay, it is the type is the face source. Okay, so you have a cell source, face source. So here is the different type available in the function object. So type wise we have a cell source, face source, field average, field coordinate system transform, field min max, okay, field value data, near wall field, patch props, process fields, okay, then set, streamline, surface interpolation, surface wall bounded streamline. So the streamline and wall bounded streamline and the surfaces we looked at with the help of the motorbike type of the test case, okay, where with the help of the surface we able to do the co-processing while the simulation going on. We can extract the snapshot and try to look at how the simulation is progress. Same way streamline plots as well as this thing is very important when we want to do the co-processing. Okay, so let's say we want to do certain operation on some of the faces. So faces normally we are interested either inlet outlet as a one of the very important patch. Okay, and here is certain few things like this is the library we have to plug in. Okay, let's say you modified the function object based on your requirement, you can customize this function object. Okay, so at that point of time you have to plug that customized library. Okay, then output control is this time steps. So per time step we supposed to write this data. Okay, so time step is whatever we defining based on the delta t. Okay, so based on that we can write the data. So here time step and writing interval is 50. That means it's not going to write every iterations, but here we required the output for every iteration, let's say. Then it is the control output control is the time step. You have a different option: runtime, time step, output time, CPU clock, and adjustable time. Okay, and then we have output interval. Every one time step you can change to every 50, 100, whatever you required. Okay, so log true, that means it also writing the log about these files. Okay, then we also have to specify the patch over which we want to look at this phase force. So phase force is related to the any of the two-dimensional boundaries. Okay, so in this is, let's say, lead driven cavity, so we are interested on a moving wall, what is happening, and certain operation you can do like sum. You can do the averaged area, average value, area integral value, area normal average, area normal integration, average, mean, max, sum, sum directional, so weightage, average area. Okay, so this is all thing you can able to do in terms of the operations. Okay, so we are interested, let's say, what is the total mass flow rate. Okay, then you can go with the sum or weightage average, area averaged, if we are looking at the average velocity on, let's say, inlet plane. Okay, so what is the average velocity? Let's say we are working with some periodic type of the domain where we coded in terms of the some lambda and different type of the solver. We not directly specifying any inflow velocity, let's say. Okay, so at that point of time, if you want to look at what is the average inflow velocity with which the flow is entering, so for that purpose, if you go with the this weightage area averaged or weightage average type of the things, okay, it give you the entire average inflow plane velocity. Let's say we define a fully developed velocity profile at the inflow plane. Okay, so when we define with the help of the equation by setting the groovy BC. Okay, and later on we want to check, let's say, what is the average velocity that I am looking at on the inlet plane. Okay, so with the help of this weightage average or weightage area averaged or average integration, all this help us to calculate all that quantities. Okay, or you can simply say sum of the everything. Okay, so it is what you want. Depending on that you can choose the operations. Okay, and field, let's say we required right now only the mass flow rate, so we specify the flux. Okay, if we are interested in the velocity, then you specify the velocity. Whatever you required on that particular patch, it goes in as a field, and whatever the field you specify for that particular field, it apply these operations on this particular patch. Okay, and the source is the phase source. Okay, why? Because we are working with the boundary patch. Okay, so like that way you can execute certain things. Same way, let's say we are interested in the min max. So when we interested in the min max values, okay, so at that point of time, let's min max, that means no operation, sorry, from the operation we supposed to choose either min or the max value, okay, and like that way we can specify the min max inside the domain, okay. Let me check, somewhere I have here min max. So first we explore, yeah, field min max, okay. So min max, sorry, no operation is required, because with the help of the min max immediately it gives us the value. Again, the type is the min max, library we have to specify, okay. Then log file is true, writing control time step and every interval, we are defining this mode component wise, okay. And field is P and U, for both we are looking at a max min values, okay. So that is one thing. Let's again go back at the top. So another very important aspect is this field averaged, okay. So when we talk about the pimple form or the piezo form with the transient, I told you that we have to do the averaging when we look at the flow become fully developed, okay. After that we do the averaging for certain number of the cycles, and with that averaged flow field we are able to compare the data. So here is the few things related to field averaged, okay. So field average type is the field average. We require this particular object file, okay. Output is the time, okay. Output control is the time. You can change the let's say you don't want field average to be applied for each time step, okay. Let's say we are looking at some phase average type of the things, okay. So who are working in the CFD, sometime we want to do the phase average. What is phase average? That means, let's say we are talking about flow or a circular cylinder. Our flow become fully developed when we see the lift or drag plot over a time. So we are looking at, okay, now in the lift or drag, consecutive peak are getting at the same level. So then we say, okay, now our flow become fully developed. But we are interested not on the entire averaging. We are interested what happen when the flow getting the peaks. So every peaks we have to accumulate for, let's say, 100 peaks or 20 peaks, and then we want to do the averaging only for that particular peak. At that point of time we can control this with the help of the this output interval. It's supposed to be what, okay. So based on the peak, so we find out the time difference between the two peaks, so that gives us the time duration, and from the time duration and based on the delta t, find out what is the time step required to reach from one peak to another peak. Based on that you can change this value, okay, and it will give you the phase averaged, okay. So it is sometime very important when we are working with the turbulent flows. So sometime people, when you read couple of paper, you come across, let's say it is not a time average, it is a phase average data. So you can handle with the help of the this way. Then there is a start time and the end time. You can from when to start and when to stop, you can do that, okay. Then we specify the fields. So in the fields we have a U and P, and you have a if you require only mean, then mean let it on, and prime to mean let it off, okay. So this prime to mean allow us to calculate the statistics, and mean allow us to calculate the time averaged flow field, okay. So when we say prime to mean on in the U field, it gives you the 6 component of Reynolds stresses, okay. And that is very very important when we want to compare with the open literature statistics. So this, with the help of this one single line, we are able to calculate or the store 6 Reynolds stresses. Same way for pressure, mean, and the statistical part, okay. So this is very simple way you can activate the field averaged inside the any of your calculation. Then this force object, okay. So force object allow us to calculate the forces on different patches, okay. So you have multiple options. So either okay, first type is the force, okay, and this file is required, libforce.so file, Okay, so we are linking dynamically inside the our calculation. Then control patch name. Okay, because when we want to calculate the force, so normally force we going to calculate on which we specify the wall as a boundary conditions. Okay, in let's say in our flow or circular cylinder, we specify the cylinder as a wall, so we only give the one patch as a cylinder. But let's say in some cases you have multiple walls, and at a time you want to calculate the forces on each of the wall, then you at a time specify the patches. Okay, so it also going to work in that line. Okay, name of the fields, so we require the pressure forces and viscous forces, so P name equal to P and U name equal to U. Based on this, it going to calculate the viscous and the pressure forces. Then density, and so density name is rho initial density. Okay, and its value is you can specify, and center of rotations. Okay, to calculate the moments. Okay, so this is all very simple setting. With the help of that you can calculate the forces on any of the solid boundaries. Okay, so but make sure whatever you specify here you apply the wall condition. Okay, so that is required. Then force coefficients, so force coefficients is nothing but CDCL values. So for that we require the reference density, center of rotation, direction of drag coefficient, direction of lift coefficients, pitch axis. Okay, that is pitch moment. Then free stream velocity magnitude. Okay, reference length and reference area. So these few things is required. So reference length is required to calculate the moments. Okay, and the reference area required to calculate the CDCL drag coefficients. Okay, so let's look at type is the force coefficients. So in previous cases is forces. Okay, and now it is force coefficients. For this library we have to include same way patch name, either cylinder or the multiple patches you can specify. P name, U name, rho in initial or infinity. Okay, init or infinity, it is the. Then we have to have a coefficient, let's say axis. Okay, rotational axis. Then we have lift direction, so in the Y, drag direction is in X, pitch in the Z direction. Okay, magnitude of incoming velocity, so this is the velocity through which the flow is approaching your obstacle. So normally whatever you specified the inlet plane, this is supposed to go there. Okay, then reference L reference is for momentum calculation, but this area is very very important. Okay, so let's say we are talking about the flow or circular cylinder. In this case this area is something like this way. You can calculate the diameter of the cylinder into the span length. Span length is what is in the Z direction, what is your domain length. Okay, so let me quickly show you how you can do this with our one of the example. Okay, so let's say this is a flow or a circular cylinder type of the example. Okay, and let me open this. So we are talking about R equal to 40 only. Okay, so very low R case, and let me check the entries in control dict file. Okay, so I specified forces and the force coefficients. Okay, and area is something like 0.2 I specified. Okay, so I don't know right now it is correct or not, so let's check how to check that that particular value is correct or not. So let's go to the paraform area. So block mesh, let me initialize the variable. Before that check mesh. So check mesh give you the idea in the Z direction. Look, in the Z direction we have a, this is two-dimensional flow. Okay, so Z direction is the span wise length of the cylinder. In the span wise length we have a plus n minus 0.1, that is equal to 0.2. Okay, and what is the diameter? So diameter give us the idea what's supposed to be the that particular area we can keep. Okay, so diameter is, okay, it's, let me see something like this way. Okay, so diameter is how much we have, plus and minus 0.5, so diameter equal to 1. Okay, so diameter equal to 1, that means this entry is supposed to be nothing but dia of cylinder into our span length in the z direction. What is the length in the z direction? So z direction, we diameter equal to 1.0, and in z direction plus and minus 1, so we have a 0.2 total. So like that way we can fix the size of this area. Okay, so this is how one can look at this reference area. If you are working with the flow or aerofoil, then chord length and the span wise direction one supposed to fix. Okay, or if you are working with, let's say, arbitrary sum of the geometry, okay, then normally people look at it as a projected area. What is the projected area? That will project on whatever the obstacle you want to calculate, lift and drag. Okay, keep that lift and that particular bluff body or the object, project that entire bluff body on the inlet plane. Okay, and whatever the area you get, it is called projected area on the inlet plane of that particular bluff body. Okay, that area you supposed to apply here. Okay, in as a reference value. Okay, and this is the reference length. Okay, to calculate the momentum, different moments. So like that way you can quickly check how you are you getting the correct drag and lift value or not. So let's quickly run this case. So this is for r equal to 40. Okay, so let me save this part. So let's run this case for steady state type of the calculation. Okay, and value of CD and CL, so definitely it is symmetric, so that's why you get a CL is almost 0. Okay, when we talk about the flow or aerofoil or something, then we able to get something different class of the lift. Otherwise for flow or circular cylinder, lift is supposed to be almost like a 0. Okay, but this CD value is something like 1.6432. Okay, so let me quickly give you the idea either that is a correct value or not. So I gave some place some in one of the tutorial I gave you some papers. Okay, so in the paper I not exactly remember in which paper, let me explore. In one of the paper it showed the value of, sorry, I closed the things. So let's explore the paper. Okay, not this one. Talk about the very low RE. I remember one paper. Okay, this is high RE paper. So later on you can explore this and try to compare. Okay, maybe here. Okay, so yeah, Reynolds number equal to 40. Okay, and CD value is something like 1.6. Okay, so that is what you supposed to get for R equal to 40. Okay, so in our case also we are getting something like 1.46 or so. So I say it is a pretty good match. Okay, so like that way you can try to calculate the RE. Okay, sorry, calculate the drag coefficients. Okay, fine. So let's go back to the area where we started. So let's open the log file. So in the log file, if you go down, okay, after the flow almost converge, we will get 1.643. okay, and here you have 1.6. so I say it is a very good pretty good result. Let's say now uh, we forgot to tune this area value correctly. Okay, I am keeping some different value. Okay, then what happened, just check. So I change the control dict file. Okay, and previous correct value is something like 0.2, but we kept, let's say, 1, okay, as a this area reference. Okay, and then we start simulations. Okay, sorry, lock mesh. Then what happened, our CD value is not going to match. Okay, because our reference area is completely different. Look, previously it was 1.6. okay, so sometime you observe that if your CD value is not matching, okay, with the open literature, then first check you supposed to do is this value. Okay, either your area reference is correct or not, or your density is correct or not. Okay, or your this magnitude of free stream velocity is correct or not. Okay, so please check this value. Okay, so either of the three value has some problem, and based on that you can rectify the problem, and you will get a correct answer. Even though now simulation almost converge, we getting 0.328657, so it is very wrong CD value. Okay, because we didn't specify the correct this reference value. Okay, so this is the check one can see very quickly, either are you getting the correct CD CL value or not. Okay, so please check these three value: ARF, meg infinity, U infinity, or the rho infinity. So these three value going to affect the calculation of the CDCL. Okay, so please check this, and you going to get a correct answer. Okay, so this is about the CDCL or the force coefficients. Okay, then as I told you, min max, domain min max you can calculate. Probes, this is very very important object. So for probe, our type is the probe, and lib sampling.so file is required, and this is the probe locations. Okay, along with that you supposed to specify the field. When you want to store the probe data, please make sure it is supposed to be output control is time step, and the output interval is every one. Okay, let's say you forget and keep 100, so it is wrong. Why? Because we required the probe data for each and every time step. Okay, we cannot skip time step in between for the post processing. Okay, so make sure when you are working with this. Okay, even for this you can skip, no problem, because at the end we require the final value only. Okay, sorry, not for this, but for CDCL. Okay, so for probe, because probe is very very important to do the post processing, so make sure that this output interval is supposed to be 1 when you are working with the time steps. Okay, same way y plus calculation you can do. Okay, so for the y plus calculations we require the type is y plus and lib utility function object. Okay, and with the help of that you can do that. Then sometime we have to do certain things. Let's say we are working with VOF type of method, and we want to look at in particular zone what is the averaged value for, let's say, our alpha as a tracker. Okay, so our source is normally goes as a cell source, because we are talking about entire domain. Okay, and our file is this file required. Okay, important aspect is this operation is the volume integrations. Okay, in the previous case when we talk about the patch, we work with the area weightage average, or surface integration and all this thing. Okay, but here we require the volume integrations as a one of the operations. So with the cell source you have different operations, and you specify the field, so it give you the weightage area averaged value of the alpha for water. Okay, in entire of the domain. Okay, so this is sometime very important when we are working with the this VOF class of the things, or let's say you are working with multi-phase flow things and we want to look at what is the entire concentration of this particular species in entire domain. So you go with the volume integral type of the things, while the simulation is going on you can look at either the concentration is shooting up or it is bounding within the limit. Okay, it gives you the idea either the simulation going in correct direction or in the wrong direction. Okay, so this all few things is very helpful to manage our flow simulations. Okay, then field coordinate system transform. Okay, sorry, but I never use this, but it try to transform the field coordinates. Okay, so from origin to some other directions. Okay, and runtime modification for field u min and u primes. Okay, so I never use, but it try to transform the coordinates system. Okay, so maybe it is required in some type of when we want to compare the data with cylindrical coordinate system or so. Okay, that is maybe it is useful. Okay, then near, so near field we can calculate the values. Okay, so near, so function object, and near wall field, so whatever the patch you specify near to that, it try to calculate the near values. Okay, so what is very close to that particular patch, and you define the distance from this particular patch. Okay, so moving wall is the patch and distance is 0.009. At that distance it try to calculate the p near and u near. Okay, so this is sometime useful to calculate the wall bounded streamlines. Okay, so at that point it's, or sometimes it's called limiting streamline, exactly what is how the streamline look like on any of the wall. So normally we know that when in the on the wall u v w all component are 0. So if you try to try to draw a streamline, it is never going to happen because all components are 0. So but then also very near to the wall, if you want to look at how the streamline profile look like, then we go with this u near as a field, and based on that we can look at the near field type of the streamline. But it if you are working with the tag plot, okay, then this quantity not required, because tag plot try to interpolate very next to the all the walls. Okay, so on the tag plot if you are doing, then even on the wall also you can able to draw the limiting streamlines. Okay, so that is few things. Then we have face object like face source, and on that we are again doing the area average and all these things for few more quantities. Okay, you can do the sum of the fees. Okay, then cell zone, same thing, volume averaged of different quantities. Okay, then processor fields, so on different processors you can calculate the fields with the help of the processor field. Okay, then read field, you can read the field while the simulation going on. Okay, so you can create new field like interpolate u, and you can read it. Okay, then same few more things. Then streamline that we look at while we talk about the motorbike. So streamline output VTK is the format, u name is equal to u. Okay, track true field is up, lifetime, and that cycle allow you to change the length of the entire of the streamline. Okay, cloud particle track with the help of the cloud, or you can define one axis, and over that axis give the start and end time and number of the seeding point. Like that way you can specify the points through which the streamline supposed to be initiated. Okay, so how solver knows that from where you require the streamline. Okay, so this start point and end point. Okay, and then we have a number of the points. Okay, within this particular start to end point, and on this main number of the point it try to seed the streamline for each one of the these point locations. Okay, near field. Okay, so this near field I told you you can calculate, and that with the help of the near field you can look at the streamline or the this wall bounded streamline. Okay, so that is for that you require this near field u near. Okay, and with the help of the u near, so first we define the u near. Okay, field, like here, okay, read field, okay, then near field, near wall field we specified, okay, u to u near, and we use that u near field, okay, to calculate the limiting streamline. Okay, so for that we have a patch, motorbike patch, and over the motorbike patch we have a something like 20,000 seeding points, okay, in on entire motorbike, and on that we use this near field, okay, and let me check the distance of near field. Streamline, no, near field, yeah, 0.01. okay, so on all the motorbike patch it goes to 0.01 in the normal direction. Try to interpolate the u into u near field, okay, and create the field. That u near field, now we name is the u name, okay, if we required. Then we use that u near field to calculate the streamlines, okay, on the motorbike patch, okay, and our seeding point is 20,000, okay, it's a cloud. So this is few things one can quickly do with the help of the function objects. Okay, so let's go to this particular page number of the user manual. So our required page number is U176. okay, so here you get a idea about entire function objects, that and its different descriptions: cell source, phase source, field min max value, field value, averaging integrations, field value data, forces, coefficients, all these things. Okay, so please go through this. You have a chance to do certain more things like verticity, q, but that is with the its utility. Okay, so we require the because this is come under the utility area. Okay, so you can calculate all this thing on any of the surfaces like verticity. Okay, everything is possible with the help of the function object. Okay, so streamline, bounded flows, okay, different thing you can activate with the help of the function objects. So few sample is also available here, okay, and it's different description. So please go through this area and it give you a very nice idea about this function object. Okay, yeah. So please walk through this 3 to 4 page, okay, along with this discussion, so it is much clear with the help of that. Okay.